Recall that we defined the cumulative distribution function of a random variable to be the function that tells us the probability of the random variable taking a value less than or equal to some number. We can extend this to a function on all real numbers. So let's do an example and graph that function on all real numbers. So for random variable x, we define this function capital F from the reals to reals by capital F of little x equals the probability that a random variable is less than or equal to little x. And we call this the cumulative distribution function of x. So for example, let's consider the binomial random variable x, where we do 3 trials and we have probability of success 1/2. So say flip a coin 3 times and count the number of heads. So let's make a table for x probability that capital X equals little x and f of little x. Now x can take the values 0, 1, 2, 3. We have at least 0 successes and at most 3 successes. But I want to extend this to a function on all real numbers, so I could put in other numbers here. There's no probability that capital X is negative x. We can't have -1 successes. The probability that we have -1 or fewer successes is 0. Now if we look at x, there is a probability, a positive probability that we have 3 failures. That'll happen if we have failure, failure, failure. 1/2 to the 3rd, 1/8. So the probability that x is less than or equal to 0 is 1/8. We could put in 1/2, so we can't have exactly half a success, but the probability that x is less than or equal to 1/2 is, well, it could be 0, so that's still 1/8. We could have 1 success. That could happen in 3 ways. We choose one of the 3 trials to be the success. 1 success, 2 failures, so that's 3/8. The probability that we have 1 or fewer successes is 3/8 plus 1/8. So that's 4/8. Then we could look at a number like 3/2. The probability that we have 3/2 or fewer successes. Well, the probability of having exactly 3/2 successes is 0, because we can't have 3/2 successes. The probability of having fewer than that successes, I guess, would be 1 or 0, so that would still be 4/8, so 1/2. The probability of having the probability of having exactly 2 successes is 3 choose 2 ways to choose the 2 trials to be successes. Success squared, failure, that's still 1/8. 3 choose 2 is 3, so 3/8. So 3/8 plus 4/8 plus 1/8. Sorry, 3/8 plus 4/8, or 3/8 plus 3/8 plus 1/8 is 7/8. Again, we can't have exactly 2.5 successes, but the probability that the number of successes is less than or equal to 2.5 is these 3 probabilities, 1/8 plus 3/8 plus 3/8, so that's still 7/8. For 3, the probability of having 3 successes is success, success, success. 1/2 cubed is 1/8. The probability of having 3 or fewer successes is 1, because we know we're going to have 3 or fewer successes. Those are the only possibilities. And then if we put in another number bigger than 3, say 3.5, then there's no probability of having exactly that many successes, but less than or equal to that, yes, we certainly have less than or fewer than 3.5 successes. So if we graph this, let's see if I have enough room to graph it. Let me graph it up here. The y-axis only has to be as big as 1 because we're never going to get a value bigger than 1. Let's say here's 3/4, 1/2, 1/4, 0. So 1, 2, 3, 4. So the probability of having 0 or fewer successes is 1/2. So at 0 we've got this value. But for anything less than 0, the probability of having that many successes or fewer is 0. We can't have fewer than 0 successes. So I'm going to put an open circle here and make this function go along the x-axis. Now the probability of having 1 or fewer successes is 1/2. But if we look at a number just slightly less than 1, then the only way to have that number of successes or less would be to have 0 successes. So that would be 1/8. Similarly, if we look at 2, the probability of having 2 or fewer successes is 7/8. So right halfway between 3/4 and 1. But if we look at slightly less than 2, 3/2 or even closer, 1.9 or something, the only way to have that many successes or fewer is to have 1 or 0 successes. So we have 1/2. And then for 3, the probability of 3 or fewer successes is 1. And if we're slightly less than 3, 2.9 successes or less can only happen if we have 2, 1, or 0 successes. And then the probability of having more than, for any number greater than 3, the probability of having that many successes or less is 1. So the function looks like this. So another random variable we looked at, which is quite different from binomial, is the exponential random variable. So the exponential random variable with parameter lambda is the waiting time until the next Poisson occurrence for some other random variable which has a Poisson distribution with parameter lambda. This is a continuous random variable. And we have the probability that capital X is, well, let me use a different letter, capital Y. Probability that capital Y is greater than a value little x is e to the minus lambda little x. So that means that capital F of little x is, so 1 minus this probability. The probability that y is less than or equal to x is 1 minus the probability that y is greater than x, which is 1 minus e to the minus lambda x. This is a continuous function of little x, and looks something like this. So when x equals 0, this is 1 minus 1, so it's 0. And then as x gets very large, the exponential part goes to 0 because of the negative in the exponent. So 1 minus something getting closer and closer to 0 has a graph that looks like this. Basically the graph of e to the negative x, but turned upside down. So it approaches y equals 1 from below. And then, so this is for x greater than or equal to 0. F of x is 0 for x less than 0. So again, we've got this function that goes along the negative x-axis infinitely to the left. So for any random variable, if we look at the limit as x goes to infinity of fx, that equals 1. So for whatever values that can take, the probability of getting less than or equal to some very, very large number gets close to 1 because all the values are somewhere. And maybe there's no limit to what the values could be. They could be infinitely, they could be arbitrarily large. But as we let x go to infinity, we're going to get more and more of them. So the probability of seeing a certain value or less gets closer and closer to 1. And then the limit as x goes to a negative infinity of f of x equals 0. Because as we go further and further to the left, we're going to be to the left of most of the possible values of x, possibly all of them. The further to the left we go, the more values we're leaving off, and then there's less and less probability of getting that value or less. The end.